This is how I study acid-base balance. pH affects all functional proteins and biochemical reactions. Normal pH of body fluids. Atrial blood is 7.4 in pH. Venous blood and IF fluid is at a pH of 7.35. ICF is at a pH of 7. Alkalosis is atrial pH that is greater than 7.45. So anything that has a pH over 7.45 is alkalosis, and acidosis is atrial pH less than 7.35. Now we have the reason why these two right here, the pH is only slightly different, is because of this. Okay? The partial pressure of CO2 is 40 in the atrial, right? Partial pressure of CO2 is 45 in the venous. Now that is why the pHs are different. That is why the pH of atrial blood is 7.4 in venous blood and IF fluid is 7.35. Okay, so as you can see here, this is a pH scale, okay? Now I have 14 on top, and then I have 0 on the bottom. 0 on the bottom indicating that acidosis, decrease in pH equals increase in the hydrogen ion. 7.0, that is the normal. 7.35 in brown, it's a systemic venous blood. 7.4 in black, it's a systemic atrial blood. 14 is alkalosis, or basic up here. That means an increase in pH and a decrease in hydrogen ion. Alright, so this equation up here is very important, okay? We have carbonic acid right here, carbon dioxide with H2O, you get carbonic acid. Now you have bicarbonate, and hydrogen also gives you carbonic acid. Now, give me a moment here. Okay, so like I said again, this equation up here in blue is very important, okay? As you can see, I have different color arrows here. We have the venous blood at partial pressure of carbon dioxide at 45, like I said earlier. That basically means we have an increase in carbon dioxide, right? Now, an increase in carbon dioxide gives you an increase in hydrogen. Again, with the pH scale, okay, again with the pH scale, increase in hydrogen means a decrease in pH, and it's acidosis. It's very acidic. So as you can see here, increase in hydrogen equals a decrease in pH, acidic. Atrial blood is partial pressure carbon dioxide at 40. Decrease carbon dioxide, you get a shift to the left. Oh, I'm sorry. Up here in the venous blood, you get a shift away. So remember, increase, you go up, and away from the increase. Now decrease, you go towards the decrease, okay? Atrial blood here is a decrease in carbon dioxide, decrease in hydrogen. With the pH scale, a decrease in hydrogen equals an increase in pH, alkalosis. Okay, so we have a decrease in carbon dioxide, decrease in hydrogen, increase in pH, alkaline. Okay, so we have the acid and base balance, right? Most hydrogen are produced by metabolism. Example would be like the lactic acid from anaerobic breakdown of glucose, ketone bodies from fat metabolism. Concentration of hydrogen ions are regulated sequentially by chemical buffer systems, which are rapid, first line of defense, brain stem, respiratory centers, which act within 1 to 3 minutes. And of course, we have the renal mechanism, which is most potent, but requires hours and days to affect the pH changes. Okay, so as you can see, chemical buffer system, right? I'm going to move over to the next screen. We have the Chemical buffer system is basically the system of one or more compounds that act to resist pH changes when strong acid or base is added. Now there are a couple actually, but we're going to concentrate on bicarbonate buffer system. The other two are phosphate buffer system and protein buffer system, but like I said, we're going to concentrate on bicarbonate buffer system. Okay, so bicarbonate buffer system, the only important ECF buffer system. Carbonic acid, salts of bicarbonate. Again, down here we have carbonic acid supply is almost limitless. Okay, and that is created from CO2 released by respiration and is subject to respiratory controls. Okay, so as you can see here, I have 2 cups of water, right? One of strong acid and weak acid to the left here. Excuse me, right here. We are going to focus on the strong acid first, okay? Now, strong acid dissociate completely in water and can dramatically affect the pH, okay? Now, strong acid like hydrogen chloride, I believe. Right? A strong acid such as hydrogen chloride dissociates completely into ions. Now, as you can see, once hydrogen chloride up here enters the water, it breaks down into ions. So it dissociates completely. So it's going to have a dramatic effect on pH. Okay, now strong bases dissociate easily in water and quickly tie up to hydrogen. Okay, now that's strong bases. Okay, now strong acids dissociates completely in water and it can dramatically affect the pH. Strong bases dissociate easily in water and quickly tie up to hydrogen. Okay, so weak acid. Now weak acids dissociate partially in water, are efficient at preventing pH changes. Again, weak acids dissociate partially in water only versus completely, and they are efficient at preventing pH changes, okay? Now, weak bases accept hydrogen ion more slowly. Now, as you can see, a weak acid, such as carbonic acid, does not dissociate completely. As you can see, as it enters the water, right, it still maintains as carbonic acid. Okay, so a quick relapse on a bicarbonate buffer system. Okay, if strong acid is added right here, okay, we have bicarbonate ties up with hydrogen to form carbonic acid here. pH decreases only slightly unless all available bicarbonate is used up. If strong base is added, it causes bicarbonate to dissociate and donate a hydrogen. Hydrogen ties up with the base, example, OH. Now we have NaOH plus carbonic acid. Alright, now pH rises only slightly. Now remember that the buffers basically is a resistant change to solution, okay? There's a limit.